Okay, let's dive into this. Imagine, just for a second, a world where ordinary sand and sheer human ingenuity are literally fused together to create the digital nervous system of modern civilization. It sounds like science fiction, right? But we interact with this system every single day. We embed it in greeting cards, we put it in children's toys, and we rely on it to run the entire global economy. In this explainer, we're going deep into the epic saga of microchip technology. We're going to explore the visionaries, the intense rivalries, the staggering feats of miniaturization, and the relentless march toward the future that built the world we live in today. But to truly understand where we are right now, we have to look at exactly where we started. And that brings us to a rather massive number, 18,000. See, before we had chips, we had the vacuum tube. Back in the early 20th century, these glowing glass bulbs were the primary way to amplify electrical signals and act as binary gates. They made radio, television, and the very first digital computers possible. But there was a massive catch. The ENIAC computer, unveiled in 1946, required nearly 18,000 of these vacuum tubes. It weighed 30 tons, and it was so incredibly power-hungry that turning it on literally dimmed the lights of Philadelphia. No joke. And worse, they were super fragile. A single faulty heat-generating tube could crash an entire calculation, meaning engineers were spending more time hunting for dead tubes than actually running programs.
Now contrast that massive room-filling machine with this word, billions. We have transitioned from 18,000 fragile, massive glass tubes to a reality where a single modern device, like the phone you're probably holding right now, holds billions of microscopic switches. And every single one of those switches is flickering on and off billions of times per second. It's honestly mind-boggling. So how on earth did we get from a 30-ton behemoth to a microscopic miracle?
Section 1. The hollow state and the spark. Early computing was facing a severe crisis. Machines were just too massive, too hot, and entirely too unreliable. The future of computing desperately demanded a different kind of brain. Something solid, silent, and incredibly reliable. Well, the spark that changed everything happened in December 1947 at Bell Labs in New Jersey. Physicists John Bardeen, Walter Brattain, and William Shockley created the very first point-contact transistor. By applying quantum mechanics to material science, this tiny little slab of germanium could amplify and switch an electrical current without needing a heated filament. It generated almost no heat and took just a fraction of the power of a vacuum tube. It was an entirely new kind of animal, and it actually earned its inventors the Nobel Prize. But there was a lingering issue. A single transistor was still just one component.
Section 2. The tyranny of numbers. So, by the late 1950s, the industry had hit a wall famously known as the tyranny of numbers. The military and the space race were demanding these insanely complex guidance systems, but every single transistor, resistor, and capacitor had to be hand-soldered perfectly every single time. It was a massive bottleneck with exploding failure points. The industry desperately needed a way to create a complete circuit as a single, solid block. And what's incredible is how two brilliant minds solved this exact problem almost simultaneously in the summer of 1958. Working all alone in a deserted lab, Jack Kilby at Texas Instruments proved the monolithic idea. He made all the components out of the exact same block of semiconductor material. Now, it was a bit messy, relying on these protruding, flying gold wires to connect the parts, but hey, it worked. Then, just a few months later, Robert Noyce at Fairchild Semiconductor had a crucial additional insight with his planar process. He realized that by laying a flat, insulating layer of silicon dioxide on top, he could just print the metallic connections directly onto the surface of the chip. Noyce gave the world a roadmap to mass production, and the integrated circuit, the true microchip, was officially born.
And this invention could not have come at a better time. With the Apollo program demanding navigation computers that could actually fit inside a cramped spacecraft, NASA poured millions into this new technology. And in 1965, Gordon Moore, who would eventually co-found Intel, made a legendary observation. He prophesied that the number of transistors on a chip would double roughly every 2 years. Now, this wasn't some strict law of physics, it was a prophecy, but it established a frantic, self-fulfilling challenge for the entire industry. The race was on to bend the physical properties of silicon to human will. Just look at how fast this actually moved. 1947, we get the point-contact transistor. 1958, the first integrated circuit proves we can put them all together. 1965, Moore's law sets this relentless pace. And by 1971, we hit a massive milestone, the first microprocessor. Through the 1960s, chip density absolutely skyrocketed. Hand-drawn masks gave way to computer-aided design.
We went from tens of transistors to hundreds, and the physical size of a transistor shrank from the width of a pencil tip down to a human hair. The silicon brain was growing new neurons at a dizzying exponential pace. Section 3. The brain on a chip. By the early 1970s, the logic built into these chips had grown so incredibly complex that creating custom hardwired circuits for every single little machine just didn't make sense anymore. The industry needed something general purpose. Enter the Intel 4004 in 1971. Think about this number. 2,300. That is the transistor count of this revolutionary 4-bit microprocessor. Shrunk down to the size of a fingernail, it could do 60,000 operations per second. Now, sure, by today's standards, its power is laughable. It's about the same as a basic pocket calculator. But back then, it was earth-shattering. For the very first time, you could bake intelligence into a standard component and just change its software to give it a totally new personality. This was the exact spark that democratized computing forever.
And this brilliantly illustrates how standard components birthed entirely new industries. Intel followed up with the 8-bit 8080 chip, which became the heart of the Altair 8800 hobbyist kit in 1975. Well, that exact kit caught the eye of a young Harvard dropout named Bill Gates, who wrote a basic interpreter for it. Meanwhile, a college kid named Steve Wozniak used a similar, cheap microprocessor to build the Apple I. The personal computer revolution wasn't sparked by a single chip, but standardizing the microprocessor was the undisputed spark plug that made the whole thing possible.
Section 4. The fork in the road. Desktops versus mobile. As we rolled into the 1980s and 90s, the silicon brain reached a fascinating divergence. The industry really had to make a choice. Do we build for absolute raw power, or do we build for battery life? On one side, you had Wintel. That's the combination of Windows software and Intel's x86 architecture. Intel was building massive, hot, fast, billion-transistor desktop brains using 3D FinFET transistors to completely dominate the desktop market. But across the Atlantic, a British company called Acorn Computers was developing the ARM architecture. ARM embraced reduced instruction set computing. It was lean, it was efficient, and it ran on a fraction of the power. For years, it stayed pretty quiet. But when Apple needed a chip for the 2007 iPhone, a chip that wouldn't melt the battery in 5 minutes, ARM was the answer. Intel optimized for a sprint, ARM optimized for a marathon, and in doing so made the entire modern mobile world possible.
Section 5. The Cambrian Explosion of Silicon.
Eventually, Moore's law began to groan under the sheer weight of physics. You can only shrink things down so much, right? As a result, instead of just making general-purpose chips faster, the silicon brain diversified into highly specialized nervous systems. We have GPUs from NVIDIA. Originally built for rendering video games, it turns out their thousands of simple parallel cores are absolutely perfect for the intense matrix math needed to train deep neural networks. That pivot alone turned NVIDIA into a trillion-dollar giant. Then you have Google designing TPUs specifically for cloud-based artificial intelligence workloads. And Apple launching the M series, creating a full system on a chip that beautifully blends CPUs, GPUs, and a dedicated neural engine into one highly efficient package. The microchip is no longer just a brain, it's an entire specialized nervous system.
But we have to ask a very serious question here. What actually happens when these features become just a few atoms wide? Because we are hitting fundamental physical limits. At this microscopic scale, electrons start to tunnel where they shouldn't. Heat becomes an absolute unmanageable demon. The traditional trajectory of shrinking down silicon is literally colliding with the laws of the universe.
Section 6. The Unfinished Epic.
To push past these limits, human ingenuity is shifting gears, looking far beyond traditional silicon at the bizarre, astonishing future of computing hardware. Engineers are getting incredibly creative. We're seeing 3D stacking, literally building vertical skyscrapers of transistors instead of just laying them flat. We're exploring quantum computing, using qubits in superposition to solve problems exponentially faster than any classical chip could ever dream of. There are neuromorphic chips, like Intel's Low-Hi, that actually mimic the spiking neurons and synapses of the human biological brain for real-time learning. And photonic chips, which process information using light instead of electrons to provide vast bandwidth with minimal energy. We are pushing way past pure silicon to replicate true intelligence. And this pursuit has elevated the microchip to the absolute highest levels of global importance. $20 billion. That is the cost of a single state-of-the-art fabrication plant today. Manufacturing is now concentrated in the hands of a few major players, like TSMC in Taiwan, Samsung in South Korea, and Intel in the United States.
The microchip has become a strategic resource globally, quite literally as precious and vital to national security as oil. It dictates global supply chains and massive government investments worldwide. Which leaves us with this profound thought from our source material. The grand, ongoing narrative of human intelligence replicating itself in a crystalline lattice. We have traveled from a 30-ton room of glowing glass tubes to microscopic skyscrapers of atoms and quantum qubits processing light. The microchip is the invisible engine of our civilization, etched from sand by light and genius. And you know the most astonishing part of this entire explainer? We are still only in the early chapters. The silicon brain is only just beginning to wake up. What will it dream of next?